Okay, so in your previous lecture, we discussed a forecast model that is called a trend-adjusted exponential smoothing. When do we use trend-adjusted exponential smoothing? We particularly use trend-adjusted exponential smoothing to decrease the error bias in one of the previously estimated model that was exponential smoothing. What is a trend-adjusted exponential smoothing mathematically? So that is a trend-adjusted exponential smoothing. Trend-adjusted exponential smoothing is estimated using three equations. So the first equation is simply the error correction version, which is given by the exponential smoothing. That is f subscript t, which is the current forecast value, that is equal to previous forecast value ft minus 1 plus something called alpha, and then it's multiplied with something called previous forecast error, which is estimated by a subscript t minus 1 minus f subscript t minus 1. So basically, in trend adjusted exponential smoothing, the first equation corresponds to what we used in exponential smoothing. The second part, however, and by the way, this first equation is once again, it's called error correction. Why is it error correction? Because if you see that actual value minus forecast value is basically an error. So this one is a previous actual value minus previous forecast value. So this algebraic expression is basically equal to previous forecast error, which is then multiplied with something called alpha. And we discussed what is the impact of alpha, what's the mathematical and what's the range which we used in forecast. That is, in forecast, we use somewhere around 5% to 75%. Why do we take this range? We discussed that because mathematically the alpha value is from 0 to 100%. So if you take the alpha value 0 or a 0%, so your forecast value simply becomes equal to what we call the previous forecast value. And in that regard, you simply get a linear line, a straight line. Next, if we take the alpha value equal to 100%, so this reverses this whole model of error correction into what we call a naive model. And what was a naive model? It's simply equal to whatever is the current forecast value is equal to what we call the previous actual value. So that's why we never take the alpha value that is close to 0 or close to 100%. We always take it in a range of 5 to 75% to minimize the impact of 0% alpha and a 100% alpha. The second equation is what we call the trend adjustment or the trend correction. So T subscript T, so T corresponds to trend, and subscript T basically means two things. This means it's in a time series representation, the data. And most of all, it's a current value, whatever is in consideration right now. That is equal to whatever is the trend value in the previous period. So T minus 1, that's the first lag, plus beta. Beta again is a smoothing constant, but this time it is used in a trend adjustment equation, mathematical, and the forecast values range of beta is exactly equal to alpha. And this is followed by what we call the current forecast value. So what is the current forecast value? It's simply the value given by the first equation minus the forecast that includes trend, but its previous value. That is the equation second. So if you think about that, this particular algebraic expression estimates what we call the value of trend. And then this trend is multiplied with something called a smoothing constant to minimize the randomness. We talked about the randomness in back in your lectures. And then it is added in previous trend. So in a manner, it's basically a trend adjustment. This equation performs a trend adjustment. Lastly, the forecast including trend, which is basically the forecast value given by this model right here, trend adjusted exponential smoothing, in which a trend is included. That is simply equal to the error correction part, which is given by exponential plus whatever is the trend value. This is the trend adjusted exponential smoothing. Now, in today's lecture, we are proceeding one step further, and we are trying to understand what we call the time series decomposition model. Now, what is a time series decomposition model? So by the way, the trend adjusted exponential smoothing is an additive forecast model, while time series decomposition model is what we call a multiplicative forecast model. What does that mean? Now, we discussed the components of data. There are three main components of data. The first one is a trend, that is a gradual upward or downward movement in data. So for example, if that is an x-axis, and usually at x-axis we take time, and that is some value. If the value is gradually increasing, then we call it trend. So this one is a positive trend, but if the value is gradually decreasing, that one is a negative trend. The second component is what we call the seasonality. Now, what is a seasonality? So from one peak to another peak, if the duration on the x-axis, which is the time, it's equal to or less than 1 year, we call such components of data as a seasonal components. And if this time period is more than a year, so we call such component, the second version of the seasonality is a cyclicity, cyclic component, which we call. That is a cyclic component. And the third component, because of which primarily you get the error, which is the random component, which is basically the sudden movement, sudden upward or sudden downward movement in data. So one thing you should always remember about so this is the trend component, that is the seasonality component, and that is the random component. So you should remember something about a random component. Each and every random component corresponds to a random event which you can't predict. So if you notice a sudden increase or sudden decrease in data points, and they are repeating themselves in the same manner, then it's no longer a random component, it's a seasonal component. And I showed you several data types in your regular lecture, and I hope you can differentiate between whatever is a random component and whatever is a seasonal component. So in time series decomposition model, we have more than one component. So for instance, we got a trend accompanied by a seasonal component. So the data on which we applied the trend adjusted exponential smoothing, there was no seasonality or no cyclicity in that particular regard, maybe a randomness, but that was primarily a trend data. So in that particular data, you can apply a trend adjusted exponential smoothing. But what if a data has two components? It has a trend, maybe a strong or a weak, and alongside that a seasonality. Then to forecast such kind of a data, we use a model that is called a time series decomposition model. Now, what happens in a time series decomposition model? As the word suggests, decomposition means breaking down. So first of all, we break down the data into the seasonality, irregularity, then we isolate the trend, and then in a particular mathematical manner, we combine the data together and we get the forecast for such kind of a data that has trend accompanied by a seasonality. In that particular regard, this is a data type, and let's plot this data and you'll exactly know what I mean. So this data is from quarter 1 2012 till quarter 4 2018, and we are supposed to apply the time series decomposition model. So let's plot that. So if we plot this data, and if I introduce a few grid lines in it, so maybe major vertical. Now, this is a peak, and which appears in quarter 1 of 2012, and then again you got a peak which appears in quarter 1 2013, since it's the fifth value right here, so we can change that and change this one. So I'll select the data type and I will tell Excel to take these values. So here you go. Now, so the first peak appears in quarter 1 and the second peak appears in quarter 1 2013. So this means the next peak appear within 1 year. Then again, if we follow that pattern, the next peak appears somewhere in quarter 1 2014, and then again a next peak appears somewhere around quarter 1 15 and 2015, and so on and so forth. So you see here, you can see a sudden upward movement in data, a sharp upward movement in data, but that pattern is repeated. So we'll not call it a random component, rather we'll call it a seasonal component, because the next peak appear within 1 year, equal to or less than 1 year. Now, talking about the trend, so if you think about a trend in a way, so if I present a trend line in a sense like this, so the data exhibits a weak trend accompanied by a strong seasonality. So this data is a perfect candidate on which we can apply a time series decomposition model. Now, time series decomposition model is basically an algorithm in which there are several steps. In first step, we are supposed to estimate what we call a baseline value. So now what is a baseline in time series decomposition model? So if you think in a manner, so if once again I present its graph, and somehow with some method, if we can dissect this seasonality, we can pass a line through it. So the seasonality will be divided into two parts. The one that comes above that segregating line, and the seasonality that is below that segregating line. So that is step number one. How can we perform that? There are several ways for that, but in order to do that, in order to estimate the baseline, so I'm going to estimate the baseline, we are supposed to use the exponential smoothing. So you people know what's the equation of exponential smoothing. So I'll try to write it right here. So here you go. This is the exponential smoothing. So that would be a kind of your revision as well. So f subscript t is equal to f subscript t minus 1 plus alpha into a subscript t minus 1 minus f subscript t minus 1. So we will use the exponential smoothing or error correction equation to dissect this data. And since you checked the trend in this data, so whenever we get a weak trend in data, we basically use an alpha value that is somewhere close to 5%. And during the model selection methodology, I introduce you to how to select the optimal value of alpha. You take it in increments of a 2% or a 5%. For instance, here the trend is weak. So let's suppose we start from a 15% and a 10% and a 5%, and then we start estimating the value of map. So the value of map that comes less for a particular alpha value, we select that. But in this case, since we are not forecasting, we are just simply dissecting the actual data, and the trend is weak. So we'll take the value of alpha that is somewhere close to 5%. So let's suppose on that particular data set, we took an alpha value that is somewhere around 7%. Now, that's the step number one. So what we should do next is apply exponential smoothing, or the equation which I just mentioned right here. So the first part is a ft minus 1. So what's a ft minus 1 in that particular regard? We take this through a naive method, which is the current forecast value. So wherever I put an equality, the whole row become time specification current. So the row above that becomes first lag, and the row above that becomes the second lag, and so on and so forth. So the first forecast value using this particular equation is through naive forecast. So it's the forecast value simply equal to previous actual value. Then we go on and apply the exponential smoothing. So exponential smoothing equation is f subscript t minus 1, which is this value. So this is current forecast. So this cell value corresponds to ft minus 1. Then we add with that whatever alpha value selected. In this case, we selected alpha value that is a 4%, and we are supposed to fix it since all the cells will get the value of a 7% alpha. So click F4. So if you click F4, it will be fixed like this, $sign, fix reference into a subscript t minus 1. So since we are in this row, and the cell behind this one is a subscript t specification, right? So this one is a subscript t minus 1 minus f subscript t minus 1, and that is the first value of the baseline using the exponential smoothing equation. And here you go. And extend it across, and you got your baseline. Now, what's the impact of that? Let's have a look. So if I plot them together, so you see this orange line, and I will remove the string variable. So here you go. So this orange line basically dissects the actual data into two parts, the part above the orange line and the part below the orange line. So the part above the orange line represents positive component of the seasonality, and the region below the orange line represents the negative part of the seasonality. Now, the next step in the trend adjusted exponential smoothing is to estimate what we call the seasonality index, and I'll simply call it SI, seasonal index. So I'll write SI here, that's the seasonal index. So I'll call it S index. Now, if you remember, what is an index? Index is something above or below 1 or 100%, right? How can we do that? In order to estimate the seasonal index, since this actual value has a considerable amount of seasonality associated with it, so we'll simply take the actual value and we'll divide that by the baseline value. We can't do it right here since we don't have any baseline value for the first observation. So we'll start it from here. So the value right here is a 0.946. Now, what does that mean? Now consider it like this. So if I consider this line and its value is equal to 1, so this 0.94 is beneath 1. So we'll interpret it in a way. We'll say that seasonality on time period Q2 2012 is 6%, approximately 6% below the baseline. So if, let's suppose, if the value was about 1.94, then we would interpret this value in a way that seasonality or irregularity is 94% above the baseline. So any value more than 1 will correspond to the positive part of this seasonality. Any value that is below 1 will represent a negative part of the seasonality. Now let's proceed with this estimation. So if we continue in that way, so what will we get? So if I extend that across, so now you see some values are below the seasonality. So once again, Q3 is below seasonality. Q1 in that particular regard is above the positive part of a seasonality, and it is about a 34% above the above the baseline, which is basically this value right here. And you can notice all these values. Some values are above, some values are below, some values are above, and some values are below the 1. So any value that is less than 1 represents a negative seasonality. Any value that is above 1 is a positive seasonality. Now, what to do after that? After that, we are supposed to estimate something called the average seasonal index. So before doing that, we need to generate a dummy variable, and let's call that dummy variable 1. So we'll give